Welcome back to Crunch Labs. I'm Mark Rober, and today we're going to be talking about the chain reaction catapult and all the juicy engineering nuggets that go along with it. And I've just got to say, I am so stoked about this one because people often ask me, like, when did I first become interested in engineering? I really do think it's when I took high school physics and I realized math and numbers and equations can help us understand and predict the world around us. So if you have like a ball like this and you throw it in the air, I can tell you where it will land. I can tell you the speed it will be traveling when it lands. I can tell you how many seconds it would be in the air. And no matter where you live or what language you speak, we'd all come up with the same answer for that prediction of the future. It's like having a crystal ball, but a crystal ball that actually works. And if you can use math to predict the future, it allows you to send spacecraft to intercept asteroids to keep them from deflecting into the Earth. Or you can use those same math and equations to figure out what you need to do to get a rover to another stinking planet. It's really powerful stuff. So when someone raises their hand in class and asks that classic question, teacher, when am I ever going to use this in real life? Well, the answer for the stuff today is all the time, because we're talking about the physics of projectile motion of something flying through the air. And I used the information we're going to learn today when I built my automatic bullseye dartboard to predict where the dart will land for the world's longest field goal kicking robot, the world's largest t-shirt cannon, the world's first rocket golf club, the world's largest trampoline, and so many more. Basically, your brain is about to grow in a bunch of really delightful ways. Let's get started. As usual, we'll start with our question of the day, and as a reminder, it's supposed to be a pretty hard question when you read it, but then after we've talked for a bit, you might be able to figure it out even before I tell you. So let's see what we got. Which hits the ground first, a dropped bullet or a shot bullet? Dang it. One of these days, my goal is to hit that camera or kill my cameraman, whichever one comes first. Let me just explain what I mean by that. Let's say I've got a gun here and I have a bullet here. If I shoot the gun at the exact same time as I drop the bullet and the gun shoots forward, which will hit the ground first? The bullet that I drop here or the bullet that's coming straight forward out of the gun? Now, for the sake of argument, assume the Earth is flat. The Earth is very much not flat, but for the sake of this question, assume that it is. All right, so then to help us answer this question, let's do some experiments. We'll start with a thought experiment. Let's say I'm in space and I have this wrench, and I throw this wrench. After I let it go, and it's just coasting through space, does it speed up? Does it slow down? Or does it keep moving at the same speed? Let me ask that another way. Let's say I had a ball here and I roll it along this table. After I release the ball and let it go, assume this is on a gym floor, does the ball speed up? Does it slow down? Or does it keep rolling at the same speed? Ignore friction. Think of like a puck on ice, right? And the answer is, as you might have guessed, it just keeps moving. That's one of Newton's laws of motion. Once something in motion, it just keeps moving unless something else interferes with it. Again, ignore friction, which is, eventually it slows down because of friction. But that's why if you're thinking in space, that wrench just keeps coasting forever because there's no friction there. All right, well, let's do another experiment in our minds. Let's go to a top of a building. This time, imagine you have a ball. Now, instead of this time rolling or throwing something horizontally, let's go vertical. So you take this little ball, you give it a little push downwards. Now, does it slow down and stop in the middle of the air? Does it keep falling at the exact same speed? Or does it speed up going faster and faster? Now, right now, you're probably being like, duh, Mark. It keeps going faster and faster. That's what happens when you drop something. And that's right. It's because of a force we call gravity. Basically, the Earth weighs so much, it's so massive, it attracts things toward it. So if you're standing here, you go this way. If you're over here, you go this way. Everything falls towards the center of the Earth. It's almost like a magnet. And if we hop in a time machine and go back about 500 years, we'd meet a guy named Galileo. He was an Italian guy and pretty important. He's the father of modern science and like the scientific method. Sort of a big deal. He was one of the first to say, you know what? I don't think it's all the planets and the sun that rotate around the Earth, but I think the sun is stationary and all the planets rotate around the sun. And that challenged what most people thought at that time, and he got in a lot of trouble for it, but it turns out he was right. And one thing he figured out, it said, is by dropping different objects from the top of the Leaning Tower of Pisa, that not only do objects go faster as they fall, the fancy word for that is they accelerate, but he figured out the exact rate of acceleration. It turns out it's about an extra 10 meters per second every additional second. Another way to say that is the distance a ball falls in each moment is the square of the time increment to that spot. So initially, if it moves 1 inch, then 2 time increments from the start, it's moved 4 inches, and then 3 time increments from the start, it's moved 9 inches, and then 4 time increments from the start, it's moved 16 inches. But don't take my word for it. Let's take a field trip. So as you can see, I've got a board here, and there's black marks on here incrementally going down. And the spacing is such that the first one's at 1 inch, so 1 times 1 is 1, then 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and it continues all the way down to 12 times 12 is 144. So now if Galileo was right about his prediction about how fast things accelerate as they fall, if we take equal time increment snapshots as I drop this ball, it should line up with each of these black lines. Let's test it out. Now that happened a little fast, so let's watch it back in slow-mo. There you go! And you can see it matches up perfectly. Galileo was right. And the best part about that is anyone could verify this, no matter what language you speak, no matter what country you live in, we would all get the same answer. Now what's really interesting is if you use these same relationships that Galileo discovered, and if you tell me how long it takes for a ball to hit the ground, I can tell you exactly how far that it fell from. And this is super cool because let's say you're cliff jumping and you're jumping off a cliff into the water, you're not sure how high it is. All you have to do is throw a rock off the cliff and time how long it takes to hit the water. And then based off that time, you know how high the jump was. In fact, right here on the board, we've got the formula. So you take the time in the air, let's say it took 2 seconds for the rock to hit the water, then you square it. That's just a fancy way of saying you take the number and multiply it by itself. So in this case, if it's 2 seconds, 2 times 2 is 4. Then you multiply it by 16, that's 64. So that means the cliff you're about to jump off is exactly 64 feet high. And then if you prefer meters, here's the formula, exact same thing, except instead of multiplying by 16, you multiply it by 4.9. And what's really interesting about this is you could even measure the height of something you can't see the bottom of. You just drop something down and then stop timing as soon as you hear a sound. Or you could measure like the height of a tree by throwing a rock up and starting the time as soon as the rock is right at the top of the tree. I actually made a video about this a long time ago. I even made a free app to go along with it. I think I didn't update the app, so it may not work, but I think someone else made a copycat version of the app that totally works. But honestly, the math isn't that challenging. So you can either use that app or just use your own stopwatch and do the math yourself. All right, so we've already proven Galileo right that an object moving freely vertically will speed up at the rate of these black lines. And then we talked about moving horizontally. Again, let's pretend either I'm rolling this or even better, we're in space. Put on your space helmets. This is exactly what it would look like if I pushed this softball forward and we took equal time increment snapshots. But now what happens if we combine the two? Well, to do that, all you simply have to do is match up each black line with the corresponding black line. And if we put an orange tennis ball at each of those intersections, you get this. This is called projectile motion. It's a parabolic curve, and it should look pretty familiar because it's the path any object follows when it's flowing freely through the air. Even something like a hose, if water was flowing from it and I turned it on here, it would follow this path because that's like a bunch of little water droplets that are like a bunch of little balls just flying through the air and curving downwards. It's just a combination of the motion moving forward at a constant rate and the motion of moving down at an accelerated rate. But my favorite thing about science is you don't have to take my word for it. We can prove that this is true. So if I take a ball and I throw it just like this, and then again, if we watch it back in slow-mo just to make sure, you can see it matches up perfectly, just like we predicted. Projectile motion is simply just a combination of the motions in both directions. And what's really cool is if you throw it back up this way, it follows the same exact path. How cool is that? And then what's really interesting is we could take the horizontal board and move it down at an angle like this, so now all the balls hang in this fashion. And then when we toss a ball, it follows the same path and the same principle of projectile motion. So for example, this knowledge was super useful for me when I did the automatic bullseye dartboard, because I knew from a top angle, the dart would follow a straight line, but from a side angle, it would follow a parabolic curve like this. So from just 100 milliseconds worth of data, as soon as the dart basically left the hand of the thrower, I could take that information and make a perfect prediction at the spot left and right, and at the perfect spot up and down to move the dartboard so I could get the perfect bullseye. This knowledge was also really helpful when predicting the landing spot for the world's largest t-shirt cannon, also for my field goal kicking robot, and my rocket powered golf club. Although those golf balls went so far, we were never able to find any of them. One fun thing is that anything flying through the air, just based off its own inertia, always follows this parabolic trajectory. But then you might be like, well, Mark, what about a human? Like, when a high jumper goes up, they're flopping all around. That's not a parabola. But a high jumper actually does follow a parabola if you look at the center of mass. Now, what do I mean about center of mass? It's basically the average location of all the stuff that makes up a thing. So I've got a broom here, and the center of mass for this broom is right about here. That means there's equal stuff on this side as there is on this side. And you could tell that because I'm balancing it right here at this point. And then for a sphere, like a basketball like this, the center of mass, the average point of all the stuff, is actually right in the middle. And that's kind of interesting because there's just air there. So you don't actually need to have physical stuff wherever the center of the mass is. In this case, the very middle of the basketball. And so then if you track the center of mass for a high jumper, you'll see it follows a perfect parabola like this. Now this concept led to a massive leap forward in the high jump world because a guy named Dick Fosbury invented a new way of doing the high jump. And before he came along, you raised your legs up to the side, sort of like this. But then he did something where you kind of jump backwards more like this. And what's crazy about that, the advantage it gives you is as you run up and then jump up and then bend backwards like this, if you actually track the center of mass, it doesn't go over the bar. It's kind of like a crazy hack that means you can get your body to go higher. Before, when they were just jumping to the side, you couldn't go as high because the center of mass also had to go over the bar. But by contorting this way, the way Fosbury did, that whole parabola stays under the bar, which is why this technique led to a bunch of new world records being set. Pretty cool. Like I said, when will you use this stuff in real life? Well, Dick Fosbury showed us in the dang Olympics. That's where. All right, so there's two more juicy things I want to talk about for projectile motion because this is just such a lovely topic. And the first is, what is the right launch angle to launch a ball if you want it to go the farthest? And rather than me explaining it right now, let's go check in with past Mark when I tackled this exact same question when I was working with Matt Prater, who had the record for the world's longest field goal kick. And one of the things Matt does so well is that technically you want to launch the ball at 45 degrees to maximize the distance on a kick. More than that, and you waste your energy in height. Lower than that, and it hits the ground prematurely. In real life though, where the ball experiences drag from wind resistance, the ideal angle is closer to 40 degrees, which you can see Prater has down to a science. This is 1 yard past the NFL record, which this man holds.
Oh, I hit off my toe. Get up.
It's good!
Is it in? I'll take it. We'll be able to go back a little further.
You're crazy, dude. Okay, so the final juicy nugget has to do with what throwing a ball has to do with space and objects orbiting Earth. And that's if you throw a rock up, it will go up, and because of gravity, the Earth sucks it back using that gravitational magnet-like force, and after going up, it comes down. Now, if you throw it to the side, it'll go to the side, and then also come down. But what if you threw a rock hard enough off to the side that it came up and came over and didn't stop falling until it made it past Earth? Well, then it would keep falling and falling and falling forever. And that's basically what it means to have something in orbit. You've thrown it so far, it sort of went off the cliff and then just kept falling. And now it's stuck in this orbit as gravity tries and pulls it towards the center, and it just keeps falling over the cliff. It just takes a lot of speed and energy to get going that fast, to get up over the cliff to orbit. That's why all launches take place in Florida in the United States, because it's closer to the equator, where you're kind of cheating and you already have a lot of speed. And just like rockets and satellites orbit the Earth, and this is exactly what the moon is doing. It's constantly falling, kind of trying to get to the center of the Earth, but it's like falling over that cliff and it rotates around the Earth in the same way that the Earth does the same thing as it orbits and rotates around the sun. It's like falling over that cliff, constantly trying to get to the sun, but just moving around it instead. Which is exactly the fact that our buddy Galileo discovered, which means we've now come full circle, and that means it's time to answer our question of the day. And for that, let's go back to the wall. Okay, so you might already have a sense as to the answer to our question of the day, which is a reminder, is if I have a gun right here that shoots a bullet straight out, and then I'm just holding a bullet, and I shoot the gun and drop the bullet at the same time, which one hits the ground first? So there's two ways to answer this question. One, which is something I like to do with brain teasers, is take the extremes. So if I point the gun down and shoot it, at an angle like this, well, clearly that bullet's gonna hit the ground before this one does, just under gravity. And then if I go the other way and I angle it up a little bit and shoot it, well, clearly this one I drop's gonna hit the ground because that one's gonna go up for a while, then come down. By using those extremes, you're like, well, that must mean there's some middle spot where they tie. That makes sense that it would be horizontal. And that checks out with what we've been talking about here, right? The two directions are independent. So it doesn't matter how fast or slow you're going forward, or if you're not moving forward at all, you're gonna fall at the same rate every time just due to gravity. But again, you don't have to take my word for it. Here's a side-by-side comparison of a ball dropping straight down and the ball being thrown forward. And as you can see, they hit the ground at the exact same time. Okay, so now that we've answered the question of the day, it's time to put this thing together. Now, as always, there's the booklet that comes with it that you could just use. You could watch this and pause as you go along. You could use them together. Either way, I'm gonna cruise through this in about 4 minutes. It'll be really quick, but for you doing this at home, it should take anywhere from 20 minutes to an hour. Let's get started. First, locate 2 long white bolts and a dark blue catapult arm. Next, slide the bolts through the 2 small holes in the wood. Then stack a yellow spacer onto each of the 2 bolts. Then slide one of the blue baskets over the yellow spacer on the catapult arm. Make sure the curve of the basket lines up with the curve of the wooden arm. Then stack a matching wooden arm piece over the white bolts and twist on 2 nuts to lock it in place. Next, use the short white bolts to attach 3 of the blue threaded standoffs to the catapult frame. Make sure to use these 3 holes on the bottom of the frame, not the ones on top. Next, we're going to mount the catapult arm and the yellow trigger arm onto the wood frame. But in order to do so, we need to make them slightly overlap. Slide the bottom of the yellow trigger arm slightly into the bottom of the blue catapult arm, and then slide them both onto the blue standoffs. Now find the red lever and place it onto the 3rd blue standoff like this. Then rotate the red lever through the blue catapult arm until it makes contact with the yellow trigger arm. And if you've done it right, it should look like this. Now use the short white bolts to screw another catapult frame piece to the build. Then slide a short wood dowel through one of the 3 holes in the frame, then use 2 black O-rings to hold that one in place. Little pro tip, this dowel controls the angle or trajectory of the catapult launch. This setting will make your catapult have the tallest trajectory, but the shortest distance. Now find a small red wood piece and peel and stick a wooden washer to each side. Then line the red wood piece up with this hole in the wooden frame, which is closest to the Crunch Labs logo. Next, use a long white bolt and a wing nut to lock the red wood piece in place. Next, find the twist tie and rubber band. Now fold the brown twist tie in half and hook it through one of the rubber bands. Then use the twist tie to thread the rubber band through the teardrop hole in the blue catapult arm. Now hook the ends of the rubber band over the cutouts in the top of the catapult. Then pull on the blue basket to test out the rubber band like this. And then fold the tab of the pressure plate until it forms a 45-degree angle. After that, slide the 2 slits in the pressure plate down over the yellow trigger arm. Then lock in the connection with the white O-ring. Now thread one end of a white elastic cord through the small hole in the yellow trigger arm. Then thread the other end through the hole in the small red wood piece. Push down on the pressure plate like this to make sure the connection is secure. Next, take the yellow catapult base and the 4 blue foam feet and peel and stick them together like this. then flip it over, then slide a blue hinge piece through each of the 2 slits in the catapult base. Lock them in place by stretching 2 white O-rings over the tabs that stick out on the bottom. Now pull the hinge piece apart and slide the catapult in between them. This bolt head should snap into the holes on the hinges. Make sure to use this bolt and not any of the others. Now it's time to start calibrating, and let me show you how to do this. To calibrate your catapult, we're going to need to adjust the tension of this elastic cord. The way you do that is by rotating this red wood piece back and forth. The farther back it is, the tighter the tension. The farther forward, the looser the tension. You might need to loosen the wing nut a little bit before you get started. First, let's start by adjusting this red piece until the yellow trigger arm is kind of close to the wood frame. This is just a ballpark to get as close. Next, we're going to check and see if our catapult will click when we try and load it. Place a red foam ball in the basket and press it down towards the base. If it doesn't click, we're going to rotate our red piece a little farther back until it actually does. Alright, so let's test it out. After you get your catapult to click when you load it, place one hand on the wood frame and then use the other, press down on the pressure plate. Alright, so that's pretty cool, but we're not done yet. Now we're going to make our pressure plate super sensitive. So load your catapult back up and grab an extra red ball. Then drop the ball onto the pressure plate and watch what happens. If your catapult doesn't go off, nudge the red piece a little bit forward and then drop the ball on it again. Every little nudge forward is going to make the pressure plate more and more sensitive. Then if you go too far, the catapult might not be able to click back into the loaded position. So you might need to back it off a little bit if you get to that point. The goal is to tune it perfectly so that just the dropping of a ball could set the catapult off. After you get the tension to the perfect spot, lock the setting by tightening the wing nut all the way. So now when you drop the ball, the catapult should trigger every single time. Alright, well nice work, but you still got 2 more catapults to build. That way you can actually do the chain reaction. And then once you have all 3 built, you can do your first chain reaction. Now all of these are on the lowest setting, which gives you a cool effect like this. Boom! But it doesn't have to go just in a straight line. You can set them up like this in sort of a triangle. And if you set them all to max power, you're going to need a little more space and it'll look more like this. And beyond that, you can play catch with yourself. You can mix up the power settings in between the catapults. You can go for really long drops. Make your way up the stairs. The point is just to get really creative so you can impress your family and friends. Alright, well as always, this is the part where we get to the engineering hustle. This is your chance to show off your engineering skills and maybe earn a little extra dessert from your parents by challenging them to a friendly competition. And in this case, I think you flex your ability now to estimate the height of cliffs. So you have the equation here. So just time how long it takes that rock to hit a ground. If you want it in feet, multiply that time by itself. So if it's 2 seconds, 2 times 2 is 4, times 16 is 64. That cliff is 64 feet high. Another thing you can do is go online and look at people who are doing cliff jumps into water and see which ones are lying. For example, in this case, it's supposedly a 100-foot high cliff, and yet when you time it with the stopwatch and do the math, it turns out it's much, much less. Finally, this is just the beginning. You will hear me say this every time, but engineering is an iterative process. You really get to learn that you're not supposed to get it right the first time. It's all about tweaking and adjusting the tension and moving things around in different locations. It'll take a lot of attempts, but then finally you'll get it working and then it just feels amazing. That's the engineering process. Case in point, here are all the different ways not to build a catapult that we learned before we finally settled on the final version. So you can see it started very simple back here. We're kind of just doing a prototype, trying to sort of understand the mechanics at work. You can see all the different lever arms we had. I won't bore you with all the key learnings, but this was a big one. Eventually we learned that if the base is rigid like this and you launch it, you can see the whole thing lifts up. So that's where in this case, we sort of switched to that pivot design. So now when it launched, that extra energy didn't go to like rotating and flipping the thing up. It was kind of absorbed in this rocking motion. And you can see that survived all the way to the final build. As far as you taking our final version to the next level with sort of the prototype 2.0, you know, on top of just getting creative with your trick shots, like making it go upstairs or bouncing it off walls, you can include other objects in your chain reaction. This is often called a Rube Goldberg machine. In some ways, this might help you because any variation from the shot, you can funnel down with objects and then it lands right on the next pad in the perfect spot. But I think it looks just, if not more impressive. 2 pro tips I'll just give real quick is that the name of the game here is reducing the errors and the variability. So you might find if you kind of put some heavy books on here or even tape them down, it'll be more repeatable in between shots. So when you line it up in just the right spot on the next shot, it returns and hits the same place. Another pro tip is this is the type of thing that's really good to put on video because if you're doing a live performance, even if you have it set up just right, you know, there's going to still be some variability and maybe 1 out of 3 works. But if you video it, you could try it as many times as you want and then you just show people the one that looked amazing. And speaking of which, if you want to show off what you've made, talk to your parents so you can post it online. Make sure you tag us on our socials at Crunch Labs so then I can see it and just be blown away by your guys' amazing engineering and creativity. All right, so that's it. Now you've earned your gear badge for projectile motion, so go put your Catapult machines together and make some cool chain reactions, and then I'll catch you next month right here at Crunch Labs. Oh, and if you're watching this and you haven't yet ordered your Build Box subscription from Crunch Labs, then what the heck are you waiting for? Visit crunchlabs.com with a parent, and once you're there, you can learn more about how it all works. Thanks for watching.